Today we're going to talk about work item synchronization. Synchronization is to ensure that some operations are performed in a predefined order. This includes command synchronization, for example using CL enqueue barrier, and also work item synchronization. Work item synchronization is important for kernel functions. Work item synchronization is not always necessary if we have data partitions that are independent. But if we have data partitions that are not completely independent, we need to have work item synchronization. We need to synchronize work items so that they can update the same data in the expected order. And this synchronization applies only to the work items in the same work group. We can use barrier built-in function to synchronize work items in a group. Using barrier, we can force a work item to wait until every other work item in the same group reaches the barrier. This is useful when work items need to finish computing an intermediate result that will be used in the future computation. We have options of using local memory fence and global memory fence. When using CL local memory fence, we specify that the barrier will affect the memory operations related to the work group's local memory. On the other hand, if we use global memory fence flag, the barrier will synchronize work items' access to global memory. We can use specific memory fence instructions to make sure that the memory operations issued before the fence will be completed before the operations issued after the fence. And for that, we have read memory fence, write memory fence, or in general memory fence. Another very important operation is the atomic operation. Atomic is to make sure that certain operations are either complete altogether or not completed at all. For example, let's say we want to decrement x by 4. Because this minor equal is not atomic, some problems can occur when multiple work items access x at the same time. Let's look at this sequence. We have two work items, A and B. First, A reads the value of x as 20. And at this time, B immediately follows the read operation issued by A, so B reads the value of x as of 20. And then work item A performs the decrementation, so 20 minus 4, A will get 16. In step 4, then work item A will store the value 16 to memory. Then at step 5, work item B also computes the subtraction. And then 20 subtract 4, we have 16 again. And finally, work item B stores 16 to memory. But we expect that this decrement 4 is performed by two work items, so the final result will be 12. However, as you can see, this sequence caused the result to be 16, which is incorrect. The reason behind this is that because minus equal is in fact three operations. First is read the original value from x, then subtract, that is the arithmetic operation, and then finally a memory write to store the result back to memory. So what is an atomic operation? An atomic operation that is an operation that cannot be interrupted. We have a whole list of atomic instructions supported by OpenCL. For example, the first one, atomic increment, and the second one, atomic decrement. So those two instructions will either increase the value by 1 or decrement the value by 1. And this decrementation and assignment is atomic because these are ensured to be atomic by OpenCL. And likewise, we have atomic add, subtract, and logic operations, AND, OR, XOR. Also, there are max, min, and exchange. This exchange instruction is interesting. For example, we have unsigned or signed integer atomic and exchange. This instruction takes two arguments. First is a pointer to global memory or local memory. It could be a signed or unsigned variable. And the second argument is a value. This second argument has to be in agreement with the first argument in terms of the data type. So what this instruction does is to swap x with a 32-bit value so that we will have this new value here updated. So this value here will be stored into the location pointed by x. And this instruction will return, the return value is in fact, that is the old value stored in the memory location pointed by x. Each of these instructions here updates scalar values in the global or local memory, and each will return the original value at the location x. Let's look at this kernel function. This kernel function is named atomic, and it takes one argument, that is a pointer to the global memory. So this will lead us to an integer that is stored in global memory. And we declare two variables in local memory, a and b, and we assign them to be zeros. The first statement is a++, so that is to increment a by 1. Well, this is a non-atomic instruction, and so it's a regular increment, as we saw earlier, and this statement will be executed possibly by multiple work items, and the result in A might be different from time to time. So a work item may execute read increment by 1 and then write the result back. Each work item may execute these three operations at different times. And because the sequence of this increment and update is unknown, so the result that in A will be undeterministic. Whereas the second line is the atomic increment. So what we do here is we increment the values in B in this local variable. Because it's an atomic increment, so all the work items will make sure that this increment will be performed in an atomic way. And finally, we assign the final result of A and B into this global buffer. Because variables A and B are stored in local memory, and each is allocated once for each of the computing unit. So let's say the host application starts 4 work items to execute the kernel. We expect that A and B will be incremented 4 times. But as we explained earlier, variable A will be incremented by 4 times, but because the increment and write to memory are not atomic, so the final result in A may not be 4. In contrast, this atomic increment will make sure that at the end of the execution of all the work items, the value in B will be 4. We can use atomic operations to implement very interesting mutex structure. Mutex is also called semaphore. A mutex is a structure enables mutual exclusion, and it ensures that only one work item can access data at a time. In typical software platforms like Linux or Windows, mutexes are very common. They are implemented as variables that can take 1 or 2 values, a locked value or an unlocked value. Before accessing protected data or regions, each work item must check the mutex value. If the mutex is set to its locked value, it means that the data structure is already being processed. If a work item finds the mutex in its unlocked state. Then it will set the mutex to its locked state, process the data, then set the mutex to its unlocked state. As you can see that this lock and unlock operation actually takes a few smaller operations. It will first read the original value from this mutex. Then you will change the state, so either turn the state from 0 to 1 or from 1 to 0. And then it has to set the mutex, so it will write the updated value of the mutex into memory. So we know that this check and unlock procedure must be performed atomically. Otherwise, two work items might find the mutex unlocked at the same time. Just like in the first example, the work item A and B, both of them find the initial value of x to be 20. To implement this procedure, we use atomic compare exchange function. This is very useful because this function performs a C ternary operator like this. It will compare the original value in the location x with the CMP parameter, and if that's true, we will assign this new value to x. Otherwise, we'll keep the same value as in the original location. So as we describe here, it checks whether the value at location x equals to this CMP argument or not. If so, it will change the value at x to VAL. Otherwise, the value at this location x will remain unchanged. This atomic compare exchange returns the original value at this location x. So we can use these several lines to implement a mutex. This if statement has a condition checking. Now first, we will call this atomic compare exchange. First argument is mutex, and the second argument, this is the compare, and this is the value. So this atomic instruction will compare the original value in mutex with this value 0. If it is 0, that means this mutex is in its unlocked state. And then this atomic instruction will assign 1, this is the value, to this mutex location. That is to say, we want to change the status of this mutex from an unlocked state to the locked state. Once that's done, this atomic instruction returns, and it will return the original value, which is 0, and this 0 will be compared with this 0 per this condition statement, and that is true. So we'll proceed to execute the instructions or functions for accessing the critical data. Once we finish accessing the critical data, we can then unlock the mutex. For unlocking, we'll just do atomic exchange mutex 0. That is to replace the value of mutex, which currently has 1, with this new value 0. As a result, now mutex will have the new value 0, which indicates this mutex is unlocked. Now let's come back to check this if statement. What will happen when we have the mutex already locked? So in that case, mutex already has the initial value of 1. So when we get to this if statement, at first we'll execute this atomic function. So this function will check the original value of mutex to compare the value with 0. This time, because mutex is in its locked state, so the value is 1. And when we compare, this 1 does not equal to 0, so we will not do the exchange. Instead, we will just return its original value, which is 1. And because this atomic compare exchange returns 1, and this 1 is compared with this 0, so this is not true. As a result, the instructions within this if statement will not be executed. And that serves the purpose of when we will back off if the mutex is in its locked state. Let's see another example how we can use this atomic function to implement a SpinLock. SpinLock is similar to a mutex, but SpinLock will keep checking the status of the mutex until it's in its unlocked state. So we'll define two functions. One is called lock, the other one is called unlock. So lock A is in fact an atomic compare exchange, A01, and unlock is simply atomic exchange. So these two instructions are the ones we saw earlier in the mutex example. So in this example, we have a kernel function called mutex. It takes two arguments. First one is the mutex, which is a variable stored in global memory. The second argument is sum. We will first check if mutex is in its unlocked state. If not, we'll keep checking that until it's unlocked. This is in fact the SpinLock. If we are able to lock the mutex, we'll proceed to the next line. And here we're going to increment the sum, and after that we will do unlock mutex. So basically release the sum for other work items to work on. And then we declare a variable waiting, and we initialize this variable to be 1. We will perform this while loop until waiting is set to 0. While we're waiting for this variable waiting, and then we will have another while loop, which is again a SpinLock, that will make sure that the sum is equal to the global work item size. That is to say, we will wait until all the work items finish incrementing the sum. In that case, we will turn this waiting variable to be 0. As you can see that we put this lock and unlock around this if statement, because when we check this, we want to make sure that this variable sum is not being accessed by other work items. So in the previous example, when the kernel executes, each work item will reach the SpinLock and wait until mutex turns to 0. When it is unlocked, the work item will lock the mutex, then increment the sum, and unlock the mutex. After that, the work item waits until sum equals to the total number of work items. At this point, all the work items executed in kernel are synchronized. One important observation is that we have to set the local size to be 1 in the previous example. That is to say, only one work item is there in a work group. What if the number of work items executing this kernel exceeds the number of compute units on the device? Let's look at this concrete example. If a device contains 16 compute units, and let's say we have 16 work items, and each in a different work group, they can all execute the kernel function concurrently, and they can be synchronized with the mutex. But if you attempt to execute the kernel in 17 work groups, then we have a problem. Because with 17 work groups, you can only map 16 work groups on those compute units. So specifically, there will be the 17th work item will stall because the first 16 work groups will wait for the 17th to access the mutex. And because the 17th work item cannot start until one of the 16 compute units is available. Okay, so let's say we have 16 compute units and we have 17 work items, and each in a different work group. So what will happen is 16 out of the 17 work groups will be mapped to the compute unit, and it will be launched for execution. And these 16 work groups, and specifically these 16 work items, will execute. But they will wait for the 17th work item to access the mutex. However, because all the 16 work items are occupying 16 compute units, the 17th work item cannot start until one of them relinquish the compute unit. But because the kernel function is designed in such a way that all the 16 work items that are already on the compute unit will be waiting for the mutex to be unlocked, then this will never happen, because the 17th work item is not going to be put onto the work units, because none of the work units is available. That was the case when we have more work items than the compute units. Let's look at another scenario. If you execute this kernel function with more than one work items in the same group, that is to say, if my local size is greater than 1, there are multiple work items in a work group. This will also cause the kernel to hang, because the work items in the same work group combine their individual reads and writes to the global memory into a single memory operation. As a result, the work items cannot access global memory separately, so they cannot lock or unlock the mutex at different times. And because of that, the mutex will not be useful in synchronizing the work items. Instead, it will cause the work items to hang. Here we show the earlier example again, where we increment two local variables. One is using atomic increment, the other one used regular increment. In the above example, we declare two variables in local memory, and then after increment, we transfer their values to global memory. This is useful for individual scalar values and vectors. But if you want to transfer a large amount of data between local memory and global memory, it is very time consuming. For large data sizes, it is more efficient for the kernel to start data transfer and perform other operations while the data transfer is being completed. And that's why we have several special built-in functions to transfer data, especially large amount of data, between local and global memory. For example, we have asynchronous work group copy. We can copy data from global memory to local memory, and we can specify the number of bytes and then associate that with the event. A few other similar APIs are available, just they differ in terms of the source and destination of the transfer. We can use different types of data, character type, unsigned, so all these are available for use in these asynchronous transfer APIs. This is the example of the asynchronous copy. We associate an event with this asynchronous workgroup copy, and it will copy some local data from local memory to global memory. The size of the copy is 10. The following one is another asynchronous copy that will copy 10 units of data from the global memory to local memory. And we associate this copy with the same event E. The first copy function returns the event structure. It's like the CL event structure used in host applications. And this event structure represents the status of the transfer. We can later associate with other data transfers using the same event, or we can choose to use a different event. We cannot associate this event with the callback function because this event is only available on the kernel side, whereas the callback function is a function on the host application. And as we can see in this example, the final instruction, wait group events, this function will have the kernel wait for one or more events structure associated with earlier data transfers.